Welcome to the module focusing on wireless network standards and security solutions. Let's start by going back in time. Wireless LANs were first introduced in 1991 in the Netherlands. Over a short period of time, they became globally sought after. The working principle behind wireless networks is identical to the principle of wired networks that we talked about earlier, or that of networks transferring data via optical signals. They also use the TCP/IP protocol stack. A fundamental difference is in the medium, the vehicle for transmitting signal. Also, the signal is no longer electrical or optical, but uses radio waves instead. A repercussion of this difference is that unlike wired networks, wireless networks share the same carrier for all computers, all hosts, that are within the reception range of the transmitter, and access point. Unlike in wired networks, a potential attacker doesn't have to run a man-in-the-middle attack, poison the ARP cache, or masquerade under a different IP address to eavesdrop on and control transferred communications. Establishing an unauthorized connection with a wireless network will remain unnoticed in most cases. It's possible to connect to a VLAN without the need for tampering with the network infrastructure. It doesn't require a physical presence in the office of a company whose network an intruder tries to break into. Any computer connected to an access point shares the medium with the other machines. This means that the data transferred over the same network, including confidential data, is in fact public. This is the key difference that separates wireless and wired networks. Whenever you connect to a Wi-Fi network and check your mailbox, or log into an important system service or a social media website, you have to be aware that all interconnected users can access your information. Security-wise, the worst scenario involves attackers taking control over the access point. They can then force you to connect to their rogue access point. This situation will be examined more closely in this and the next part of this course. Now we'll introduce you to wireless communication standards. Standard 802.11, the Wi-Fi standard, is in fact a set of standards. The first 802.11 standard had a maximum data rate of 2 megabytes per second. There's one thing you need to know as far as standards are concerned. Since Wi-Fi networks are standardized, they use the same frequency bands everywhere in the world. In contrast to CB radio or amateur radio users, we don't have to file for a permit to use a particular frequency spectrum. The same wireless card used in Europe will also work in the US, Asia, or Africa. This is made possible through the implementation of wireless standards. The original 802.11 standard was quite soon replaced with its B version. This version is fully retroactively compatible. The amendment increases wireless network throughput to 11 megabytes per second. Version A was released simultaneously with 802.11b. It's quite less popular as it is not compatible with version B or with the original standard. Its strength lies in employing a different signaling method. It also uses a higher frequency. The frequencies that can be seen in the chart in the picture are approximates only, because each standard uses a specified number of channels. Depending on a country, there can be 11 or 13 channels. Adjacent channels can overlap. You need to realize that, for example, for the B version, the frequency is never exactly 2.4 GHz. The successor of B is the standard 802.11g. It's used in business and homelands even today. It's retroactively compatible with the B version and the original standard. 802.11g can transmit data over a relatively long distance with a speed of up to 54 megabytes per second. Between 2004 and 2005, the N version of the standard was introduced and gained popularity. What gave it an advantage over the previous versions was the improved reliability and extended range of the wireless transmission. In 802.11n, the same signal can be transmitted and received by multiple antennas, or access points. Originally, the 802.11 standard used not only radio waves to transport data, it also defined infrared transmission. This standard, however, failed to achieve popularity and was supplanted with other technologies. Let's now briefly discuss the working principles of wireless LANs. To set up a connection with an access point, we need to determine a channel number, which is the frequency of our access point. Many access points might share one channel at a time. This means that there has to be a supplementary mechanism to identify and correctly associate the APs. This can be provided by Service Set Identifiers, SSIDs. An SSID is the name of a wireless local area network. It's not a mechanism for authenticating wireless clients. It's a standard-defined mechanism that allows a client to uniquely identify an access point for connection. This implies that SSIDs have to be public. They can't be encrypted or secured in any other way. If they were, they wouldn't deliver the functions defined in the standard. It's quite pointless to turn off SSID broadcasting, and as we will soon discover, you can't simply turn it off. If you wanted to secure your home VLAN by turning off SSID broadcasting, this could lead to the computers of your users to automatically try to connect to all access points that are available in a given area. As an access point is not broadcasting its name, the client will actively send requests to available APs for their SSIDs. This action, which is complemented by sending certain authentication data during the probing, means that disabling the SSID broadcast can lower the overall network security. It will definitely not work to tighten the security in any way. Turning off the broadcasting doesn't mean in this case that it will be harder for intruders to connect to your network. It's a behavior that can actually actively compromise a Wi-Fi network. We'll look into this more closely. Wireless client configuration is relatively easy to set up. For all operating systems, it's enough to simply choose an available access point and a creator, or a graphic interface will set up the connection. Configuration can be as easy as submitting a password, provided that the authentication is based on a pre-shared key mechanism. To facilitate connecting to a network even further, the Wi-Fi Protected Setup (WPS) protocol was developed. At this stage, access point protection is essentially safeguarding the AP's external registrar PIN. Setting up a connection is only possible if you provide the correct external registrar PIN. The key is usually printed by a manufacturer on a sticker on the device. This helps to automate the configuration and launch of the devices. A problem turned up in December 2011. It transpired that an access point could be made to disclose information on its number. Answering an external registrar PIN query, an access point reports which half of the submitted PIN is invalid. Note that the last digit of the number is its checksum. This is not a secret. You can extract a checksum from the known information. Knowing this, the PIN length is even more reduced. Being able to separately attack the two halves allows for a greater chance of cracking the PIN than in the case of having to determine the entire number at a time. The complexity of computing is worlds apart for both instances. The first part of the number requires as many as 10 to the 4th power attempts to be successfully cracked. Because of the checksum, determining the other half requires only 10 to the 3rd power attempts. Access points enforce no limit of failed attempts. Even if a client is submitting a wrong external registrar PIN over and over again, it won't provoke a reaction. The AP will still give out hints, for example by telling the client that the first half of the PIN is incorrect. This means that a successful attack requires only a degree of patience. Depending on the connection rate, it usually takes up to several minutes to crack an external registrar PIN. Once an attacker has determined the number, he can connect to an access point and be granted admin status. This means that he can change access point configuration. Unfortunately, not all access point manufacturers took steps to solve this problem or took them too late. Not all of them disabled this feature that, as you've seen, allows attackers to effectively determine external registrar PINs. What can we do as users to enhance the security of our home networks, since this is a problem that relates mostly to home networks? We need to disable the Wi-Fi Protected Setup entirely. By taking a few minutes to manually configure access points, we do a lot to improve the security of our networks. Wi-Fi is not the only wireless technology. Wireless has a long history behind it. The first developed technology was the analog network known as CD-PD. This cordless data transmission method is practically discarded today. The successor of CD-PD, GPRS, is on the other hand still employed in a variety of applications. It is now mostly used in mobile web browsing services. The technology is still also used by the WAP protocol. Another wireless technology that is extremely popular today is Bluetooth. But even given this notoriety, it is virtually unsecured. All laptops and smartphones today have a built-in Bluetooth connectivity. This technology is freely available, and the technologies that make possible the interception of data sent over this channel are equally available. The slide above shows pictures of 3 such tools. To secure your transmissions, you can only force the encryption of exchanged data. Other than that, the natural security is provided by the short maximum range of Bluetooth, a distance of 10 meters. We assume that in the 10-meter radius, there are no attackers who'd want to capture the data we exchange between the smartphone and a laptop, for example during the synchronization of an address book. RFID is another wireless technology that is spread over the world. It can be encountered mostly in supermarkets and other shops. This standard is used to tag products. Reading tags discloses the information contained in it. RFID is practically unsecured. The only protection involved assumes that a person who scans an RFID code is authorized to do it. This doesn't always have to be the case. Imagine that if a thief of an RFID reader takes it to walk around a supermarket car park. Coming closer to the cars, he's able to view the bought items that are inside. RFID's wide popularity does not ensure it is safe. You should remember that there are risks and threats connected to this technology that might be exploited by attackers. The same is true of near-field communication, NFC. It's usually used in an active-passive communication mode. This means that a near-field communication client doesn't have the power source of its own. NFC clients include, for example, the increasingly popular proximity cards. The security of near-field communication is also based on the assumption that there aren't any people around who would want to read your card. In this case, around means in the radius of up to 3 centimeters. The new release of Backtrack includes a set of tools for attacking both Bluetooth networks and NFC devices. These tools are capable, for example, of duplicating proximity cards. If on a train or bus your card is placed within 3 centimeters from a device that can read cards, an attacker can use this to duplicate the credentials saved on your card and use them without any control. Remember that there are no built-in security solutions in NFC. You can physically control medium access, provided that the medium is physical. You can, for example, monitor network cables and switches and in this way prevent unauthorized connections to your wired network. This security technique is practically impossible with wireless LANs. Usually, to be able to connect to an access point, you have to be up to 100 meters away from the AP. This is dependent upon the used antenna. The bigger it is, the better. A directional antenna can be used to reach an access point that is 100 kilometers away. This distance means that a potential intruder can attack your network even from another city or another country. Despite this, he can logically connect to your business LAN. What can you do to reduce this risk? Internet standards organizations puzzled over this problem in 1999. The WEP standard was ratified in that year. We'll come back to that later. The ratification of WEP made a lot of people sigh with relief. There's a ready privacy solution providing security that is equivalent to that of wired networks. You can now control medium access. This illusion of security was shattered 2 years later by Peter Shipley at a DEF CON convention. Shipley started the ward driving trend. This attack method consisted of searching for VLANs during recreational walks, drives, rides, or even flights with a running laptop equipped with a Wi-Fi card. There used to be geolocation maps on the internet that revealed the presence of LANs. Today, internet access in many countries is practically everywhere, and it's often free. This wasn't the case 15 years ago. The DEF CON lecture also brought positive effects as it highlighted the problem of wireless network security. Since we can't control medium access, we should above all focus on ensuring the confidentiality and authenticity of data exchanged over wireless networks. The diagram in the picture above shows which OSI model layers can be protected with security implementations. You can remember from previous lectures that the lowest layer that can be efficiently protected is the network layer. IPsec can be implemented in the third layer. IP version 6 has its protocol as a default component. Unfortunately, the layer is too high. We would have needed to control medium access and ensure the authenticity and confidentiality of data even lower. This is when WEP protocol and its successors, WPA2 and WPA, were developed. WPA and WPA2 are completely dissimilar technologies and protocols. WPA was introduced because WPA2 was too good for its times. The majority of devices used at the time were incompatible with its technology. To make people move away from WEP, WPA was introduced. The standard is compatible to some extent with WEP. Most older devices that were designed with WEP security in mind could run with WPA, but not with WPA2. Before we move on to those security solutions that fulfill their promises, it'd be good to mention those that don't. Disabling SSID broadcasting has already been brought up. Even if we turned the broadcast off, the SSID would still be emitted. SSIDs are in clear text in probe request, probe response, association request, and reassociation request packets. You can't hide it. The first thing I'd like you to remember from this course is a warning not to turn off SSID broadcasting. At best, this will not affect your VLAN security, but if you're less lucky, you can decrease the security substantially. Static IP addresses can also be used to enhance security. Almost all access points provide DHCP server services. This means that they allow connected clients to automatically configure the IP protocol. DHCP servers, however, are definitely not built with security in mind. It would then seem logical to disable the server. This, however, does little to improve security. Even though in this case an attacker who connects to an access point would have to manually configure IP address and default gateway, the information needed for configuration is transmitted by an access point in clear text in UDP packets. UDP is a broadcast protocol and can certainly be received publicly. This method only manages to delay an attack by a minute or two. The third solution is a MAC address control. As you can see in the picture above, all access points support adding a trusted MAC address list. This method is sometimes exaggeratedly referred to as a MAC address-based authentication mechanism. What it really amounts to is simple filtering. As you know from previous lectures, it's very easy to change a MAC address. It's just as easy to capture it as it's not secured in any manner. We're in OSI Model Layer 2 occupied by WPA, WPA2, or WEP. These security measures protect data transmitted in upper layers, but not in the second layer. Enabling the filtering of MAC addresses will simply make your life harder. In large VLANs, there are many different Wi-Fi clients. For example, people from other branches of the company. The MAC address whitelist should be updated manually. There's no automatic mechanism for that. Keeping a network like that would consume enormous amounts of effort and time, and the security benefits that come with it are negligible. Another approach you might come across is that since we can't control radio wave access, we should at least try to reduce the range of reception. You can do this by lowering the strength of the signal emitted by access points. You can also use special paints to coat the rooms that contain access points and servers. These paints are quite expensive, and it's doubtful whether they're truly effective. They do block out transmitted signals to some degree, but they don't warrant that an outside user will not be able to connect to your access point. Artificially reducing access point signal strength only makes it difficult for authorized users. They'll have problems connecting to a network. An attacker can always afford a bigger antenna. And we're back to the rule. The bigger the antenna, the better. Let's now take a look at Wi-Fi networks authentication methods. There are 3 authentication options. Access points might perform authentication without verifying user identity. If that's the case, anybody can connect to the wireless LAN. User identity can be verified through checking if they know a shared secret. Keys are usually submitted while a client is trying to connect to the protected network. It's crucial that you understand that these two are completely different technologies. One is used for authentication. We're talking about that now. The other ensures the confidentiality of data. We'll cover this in a moment. The third wireless authentication method involves the use of a radius server and 802.11x protocols. We've already talked about this set of protocols. To quickly remind you, in this case, an access point is configured as a radius server client. Using the EAP protocol, the radius server forwards the client-submitted authentication credentials. The server verifies the user's identity. If you use a radius server and the 802.11x protocol, shared secrets are not used. Each user has his own password. He logs onto his account and his identity is verified. This solution is both more secure and more functional. The 3 authentication methods can be used together with various encryption methods. Not all combinations will be a good fit, but you can try several of them. We've already mentioned open system networks that don't perform user verification. This is a part of the 802.11 standard. It's enough to submit the name of an open network and connect to it. A network name field can also be referred to as an SSID or a network identifier. They signify the same thing. The legality of connecting to other people's open wireless networks varies depending on a country. In the Netherlands, for example, an active intrusion to a protected wireless network is not considered a crime. It's similar for Germany. While it is a crime there, it's seen as the fault of the wireless service providers who jeopardize the safety of their customers by providing them with insufficient protection. In the majority of countries, however, it's the attacker who will be held responsible for the act. In the case of open networks, the identities of users and computers are verified against the MAC addresses of network cards. An open wireless network can also use encryption for transmitted data. Web security is used for this purpose. Open system authentication with web key encryption means the validity of the web keys will not be verified. Since frames are encrypted with this key, an access point will reject the frames that can't be decrypted. The second protection measure is using a pre-shared key. It's a hugely popular authentication method in home LANs. Before I move on to describe how clients are authenticated, I'll talk a bit about the drawbacks of this solution. If more than 2 persons share a secret, it's no longer a secret. A key must be submitted in all computers that want to establish a connection with a given wireless LAN. There's no mechanism for that, so we do it manually. That's why we will probably never change a set key. A shared secret which is not a secret and is never changed doesn't guarantee any security. We'll discover this in the second part of our module. Leaving aside the questions of authentication effectiveness, let's now see how this process looks. The technique makes use of the challenge and response mechanism we already know. A client attempts to contact a selected wireless LAN. An access point generates a pseudo-random challenge message and sends it to the client. The client has to then encrypt the received challenge with a pre-shared key, PSK, and send the encrypted response to the access point. Next, the AP decrypts the ciphertext and compares it against the challenge it sent earlier. If the results match, this means that the same key was used to encrypt and decrypt the message, implying that the client was in possession of the key and was authorized to connect to the VLAN. The system for sending challenge and response messages is not protected in any way. Note that the key itself is not transmitted over a network. Only the data encrypted with the key is transmitted. When you examine threats related to Wi-Fi security, it'll turn out that the process can be reversed. By intercepting the challenge and response messages, we can extract the PSK. Since all users share the key, all users share also medium access. In those VLANs that use PSK user authentication, all users have access to the same medium. This is like being in a local area network connected with hubs. Packets are received by all clients. It depends on the mode used by the receiver's network card to reject the packets that aren't addressed to it, or to choose to intercept and modify them. The only secure method for verifying wireless network user identity is provided by the use of the 802.11x standard. If you configure an access point as a radius server client, you will need to submit a shared secret. In this case, the secret will be shared by the access points in the radius server, and not by the X network users. This will allow the AP to check the identity of users who want to establish a connection. Each person will have their own identity. Each person will have their own secret. For example, the password stored in the Active Directory. This means that the radius server will be an Active Directory server client. It will forward questions usually according to this pattern. First, it will ask whether the user who claims to be Bob has already submitted a correct password. The next request will ask for proof that a given user is authorized to connect to an office VLAN using Wi-Fi. A more secure version of this mechanism verifies the identity of users or computers against their certificates. This does seem very complicated. Other than an access point, you need a computer used as a radius server and also a domain controller for this. As you see, the infrastructure is extensive. This is why this solution is not generally deployed in home VLANs. While it does bring a lot more security, it's excessive if there are only 3 or 4 users in a home network. As for business VLANs with 5 or more users, however, I'd strongly recommend configuring a computer as a domain controller or as a radius server. We'll see that this solution will secure a network against all known attacks. Let's now move on to the security measures for ensuring data confidentiality. As we've said, the first security measure developed was WEP. A WEP key is indirectly used not only for secure data, but also to authenticate computers. An access point doesn't decrypt frames it can't decrypt. If the frames were encrypted with an incorrect WEP key, they will be rejected. What are the flaws of the WEP technology? One of the fundamental rules of cryptography is that one key should not be reused frequently. The more often you use the same key, the less secure it becomes. The WEP standard doesn't define any solutions for automating key generation. If you wanted to change a key, you'd have to do this manually and separately for each computer. As a result of this, keys are rarely changed. The encryption used in the WEP standard is weak. The process can be seen in the picture below. It's necessary to calculate the checksum of the packet first. It's an ordinary CRC checksum, not a cryptographic hash function. This means that the WEP-protected packets are vulnerable to tampering. An attacker can modify the content of a frame and forward it by calculating the correct checksum. The checksum is added to a sent packet. We've mentioned already that this is not secured in any way. The RC4 stream cipher is used for encryption. We'll talk about this cipher at the end of all modules. The secure use of the RC4 algorithm is based on the rule that the key shouldn't be used more than once to encrypt the same data. If this rule is flouted, breaking the ciphertext is trivially easy. RC4 is based on XOR operations. Let's leave aside cryptographic details for a moment. The same data is exchanged repeatedly over the network. This transmission doesn't relate to people visiting the same website. It's about packet headers having a set structure. Predicting field values of the headers is very easy. Given this, randomization was required to improve security. In this case, randomization is provided by the presence of an initialization vector, IV. Unfortunately, it's just 24-bit. A 24-bit IV is too small. This doesn't end the list of problems, though. We'll return to that soon. When an IV is used, data stream has to be mapped with a key stream. The exclusive, or XOR, is used for this purpose. The end result is a ciphertext, or the encrypted version of a packet that we send to an access point. Key length depends on a WEP version. It can be 64-bit or even 256-bit long. Even if the key is really long, it can't ensure the security of a network on its own. This is due to a small number of initialization vectors. There's only 16,777,216 available IV values in a pool. The problem is that the risk of repeated values, the risk of collision, is much higher than it would seem at first glance. It's enough to capture more or less 5,000 packets for the risk of finding 2 packets encrypted with the same IV to be over 50%. And having the same vector equals having the same key because, as we said, WEP doesn't support dynamic key change. This means that we've managed to capture data encrypted with the same key. All it takes now to extract nearly full information on the key is to combine the ciphertext using XOR. Implementation of this weak security mechanism is even worse. The standard doesn't specify the entities responsible for generating IVs. This has to be done by a network card. How? The standard doesn't say. Initially, network card manufacturers used the following system. 1 was for the IV for encrypting the first packet, 2 was for encrypting the second packet, 3 for the third. It was highly predictable. This means that there can be attacks that consist of assuming a specific value of a vector. You can also encrypt data but not encrypt headers. In that case, an attacker is not only able to capture physical addresses of the client he's eavesdropping on, but he can also modify them. He can control the packets transmitted in this network. We've talked about the potential problems connected to adding up checksum to packets. This issue will be noticed, for example, by Korek and others. If we add a checksum to an encrypted packet, there's a one-to-one relationship between the checksum bits and the ciphertext. By modifying any checksum bit, you can determine the validity of any part of the packet. The checksums will or won't match accordingly. An access point rejects the packets that have an incorrect checksum. This is a basic mechanism for maintaining reliability of data sent over wireless networks where there's a lot of interference. You can modify a ciphertext byte by byte, modify the checksum and see if an access point rejects the packet. This will help you make sure whether or not you have correctly cracked the valid combination for the key for each part. The RC4 algorithm is vulnerable to revealing certain relationships between the key and IV. How can all of these problems be solved? Don't use WEP to start with. Look at the alternative solutions. WPA was ratified by Wi-Fi Alliance in 2003. As we mentioned, this was an interim solution. The name is a bit misleading. WPA2 suggests that it's the improved, more secure version of WPA protocol. It's the basic version of WPA instead, one that did not catch on. Users and manufacturers had to be encouraged somehow to move on to the new standard. WPA was replaced with WPA2, and it was decided that the interim version will be called WPA. Because it's essential to ensure maximum retroactive compatibility, we need to use similar security solutions. That's why we still use the RC4 algorithm. To enhance security, we extend the IV from 24 to 48 bits. This is a significant change. We also eliminate the problem related to the lack of dynamic key change. We introduce the TKIP protocol that allows the automatic generation of keys. WPA verifies the identity of users, authenticates them not only against the pre-shared key, but also using the already mentioned Radius server. The last problem that was noticed and fixed related to data integrity. Instead of a CRC checksum, the protocol used a cryptographic hash function. This function makes it more difficult to modify packets without affecting checksums. The first version of WPA is vulnerable to attacks. Most common WPA attacks target pre-shared keys. Since cracking them by going through all combinations through brute force attack, exhaustive key search, wouldn't be cost-effective, dictionary files are used for this purpose. If for some reason you need to use the WPA in the personal mode, in the pre-shared key mode, this key has to be long and complicated. Don't shrink from providing 63 random characters as a key. The key should not be found on any dictionary or word list. It should not be a simple permutation either. Adding 1 at the end doesn't do anything to improve the security of a key. Let's now briefly discuss WPA2. This protocol uses Radius servers. As far as wireless networks are concerned, this is a real revolution. The RC4 algorithm, which is vulnerable to incorrect implementation, is replaced with the advanced encryption standard. Additionally, each frame is encrypted 10 times using AES. This solution is known as CCMP. A brute force attack on the frame, a WPA2 protected packet, would take over 2 to the 100th power operations to succeed. This is practically impossible. The protocol makes use of a long, random, and unpredictable 48-bit initialization vector. Key management is automatic and native. You don't need a TKIP for this. How can you break into a WPA2 network? It takes the same methods that need to be used for a WPA network. There are essentially 2 classes of attacks. The first class utilizes, for example, the processing capacity of graphics cards that scale very well. You can run multiple operations at a time if a computer has more than one well-equipped graphics card with CUDA. The processing is complex, so it might take a bit. You can also try to guess the key. This works to limit the territory of an attack to a PSK-protected network. This will prove effective if the key is easy to determine. Now a brief comparison of the 3 technologies, WEP, WPA, and WPA2, or the 802.11x standard. WEP, like WPA, encrypts packets using RC4. Unlike WEP, WPA dynamically changes keys and has a stronger IV. WPA2 uses the CCMP version of Advanced Encryption Standard for encryption. The same protocol is also used for automatic key exchange. As you'll see, the solution is a great way of ensuring VLAN security. The security of VLANs, much as the security of computer systems, is optional. It's our task to choose appropriate technologies. For standard networks, there's of course many more technologies to choose from. Each technology protects a given layer and they're less conspicuous. For wireless networks, the situation is much more simple. A wireless network administrator responsible for security has to make 2 simple decisions. Select a method for authenticating users, this should be done through a Radius server, and choose a method for ensuring the confidentiality and authenticity of exchanged data. The WPA2 technology should be employed for this. Selecting these 2 options will practically guarantee a very high level of network security. Thank you.